Hello everyone, today is the 41st day of Leetcode 75 challenge. Let's begin with the 41st question. Question 700. Search in a binary search tree. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given the root of a binary tree. Fine. With binary search tree. You are also given an integer value, which is val. Your task is to search for a node in the binary search tree or BST whose value is equal to val. Okay, so basically you are given a binary search tree and you have to find the node which is equal to the given val. Suppose this is equal to the given val. If such a node is found, return the subtree rooted at that level. Suppose if this is the node, then we will return this particular subtree as the answer. If the node is not present in the tree, we return null. The final output should return the root of the subtree or null based on whether the value is found or not. So we basically just have to find the node which is given in the value, and if it is there, we have to return that particular subtree. That's the simple question understanding. Now let's go to the constraint. The number of nodes in the tree is in the range from 1 to 5,000, and the node value is from 1 to 10 to the power 7, and root is a binary search tree. Okay, and value or the value which will be given to be searched in the given BST is from 1 to 10 to the power 7. I hope you understood this problem explanation and constraints. Now let's move to the next slide. Let's understand the input output of the problem. Okay, let's take this first example. So here value is given as 2, right? So in this tree we could see 2 is here, right? So we have written this particular subtree after finding it. So output is 213. And here the value is 5 to be searched. So in this complete binary search tree, there is no 5, right? So we return none or the empty array. So this is the input output explanation. It is pretty simple and straightforward. You just have to find the node and you have to just return that particular node root. That's all. Now let's move to the next slide. Before going into the further slide, let's understand what is a binary search tree. If you already know about binary search tree, you can skip this particular part and move forward. Otherwise, please stay in. So a binary search tree is a type of binary tree where all the values in the left subtree are less than the node's value. For example, let this be a binary tree. So this is a binary tree, for example. Okay, we know the concept of binary tree, but here if you can see, all the values in the right subtree are greater than the node's value. Okay, this property helps efficient searching, insertion, and deletion. So let me make you understand. Suppose this is a root node, and if you could observe in the left subtree of this particular node to the this particular node, and to the you could see that 8 is smaller than 10, 7 is smaller than 10, 9 is smaller than 10, right? Then if you come to this particular subtree, you could see this is smaller than the node, this is greater than the node. Fine. So what binary search tree says that for every node, the left subtree for that particular node will have all the values smaller that particular node to that particular node, and the value to the right subtree of that particular node would have all the values greater to that particular node. So if you could see, here is 10. All the values in the right subtree of this 10 we have greater than this 10, right? It is 12, 11, 13. So similarly, if you go to the more subtree, if you come to this particular subtree, you could see if taking 12 as the root node, you could see 11 is smaller than 12, but 13 is greater than 12. Similarly, if you go up, if you could see 10. 10 is smaller than 12, but 11 is greater than 10, but smaller than 12, but it is in the left subtree of 12, right? Similarly, in the left hand side also 8. 8 is there, and to the left it is 7, but to the right it is 9, but 9 is smaller than 10. So everything to the left subtree will be smaller than that particular node, and everything to the right subtree will be greater to the particular node. That is what a binary search tree is. And how it works, we start from the root node. We For any operation for insert, search, or delete, we compare the target value with the current node. So suppose a target value would have been given to you. Suppose it is 3 or 10, whatever, right? Let it be 8. Okay. If the value is smaller, we move to the left child. This helps in what? Let me tell you that. The value is smaller, we move to the left child. Suppose we have 8, right? If you're standing in the root node, you can easily check, okay, we have 8 to be searched and 8 is smaller than 10. So it is a knowledgeable thing that we don't have to go to the right subtree anymore. We will just be going to the left subtree for figuring out the value, because in the right, every value would be greater than 10, right? Which will be, of course, greater than the value 8. And when you come to the left subtree, you will be knowing, okay, we have the 8 here. So this is what we were searching for. Even though if the 8 was not present there, suppose it was 9, okay, to be searched. So here you would have checked, okay, since this is 8 and the given value is 9, you might have moved to the right subtree, excluding the left subtree traversal, and you might have moved to the only the right part. Okay, and we repeat until the value is found. So this way the efficiency is much more. As time complexity in average case comes out to be log n because we basically are dividing it by n by 2, okay, in every iteration. And worst time complexity could be O of n when tree becomes skew trees. And what is a skew tree? Skew tree is which does not have both the childs. So if this is a skew tree. So if we have to find, suppose you had to find 6 here, right? So you have to traverse complete tree to get that particular 6. So in worst case it becomes O of n. And space complexity becomes O of h, where h is the height of the tree for recursive operations. Okay, that is all. That is all about binary search tree here. Now, where binary search tree is used. So I have put down some of the problems where you could use binary search tree, which is fast searching, inserting, and deletion. Okay, use when you need efficient operations on dynamic sorted data sets. For example, search or insert value in binary search tree, Leetcode 700 and 701 questions. Okay, find the minimum and maximum values or the next larger or smaller element. You can use BST ordering to quickly find those values. Find in order successor or predecessor. These are the questions you could solve. And thirdly, finding LCA in a binary search tree, you could use this, and it makes the complexity much more efficient. Now, validate or serialize BST also, you could use the concept of binary search tree, verifying the integrity or saving the restoring tree structure. Find the k smallest or largest element. We can use in order traversal to get the sorted data for order statistics. Because if you know in order traversal, and when you do the in order traversal of a binary search tree, you always get a sorted order from in ascending form. Please keep that in mind. Always you get ascending order values when you traverse the binary search tree in order traversal. So this way you could find a k smallest element, k largest element, anything you want, right? And balanced BST or guaranteed performance is basically using self-balancing BSTs to maintain log n time worst case, such as AVL or red black tree implementation. So these are the few of the implementations of the binary search tree you could go through to make your concept much more stronger and much more efficient. So I hope you understood the concept of binary search tree. Now let's move to the next slide. To understand what problem was asking, we should build up an intuition to the problem. Fine. Let's do it by understanding the goal first again. We are given the root of a binary search tree and a target value. Fine. I have just drawn a random tree for you with no values in it. Okay. Our task is to search for a node in the BST such that its value is equal to the val which is given to us. Okay, this is understandable. If such a node exists, we return the subtree rooted at that node. So basically, we just do return node. That's all. Not node value, just node. Okay, so what a brute force solution or approach could be if you don't know the concept of BST or if you don't know how to iterate in a BST, would be perform a complete traversal using BFS or DFS. Okay, so find a node you will be using BFS or DFS, and that I mean we know that BFS and DFS takes O and time complexity in worst case. Okay, and checking each node values until you find a match. However, this ignores the BST structure and takes O and time regardless of the tree shape, making it inefficient. So even BST traversal could only be applicable if you are given a BST tree. So if you are given a BST tree and if you are trying to do BFS to it, breadth first search traversal, without using the concept of BST, it is no use. It is of no use. You will be taking O and time complexity for it, right? So it's not a beneficial one. So what could be the efficient way? We use the BST property for any node. Values in the left subtree are smaller, we know that, and values in the right subtree are larger. We know this thing, right? So this will reduce the time complexity and the traversal. And instead of searching all the nodes like we do in a binary tree, we can narrow down the search using this property. So we could use the concept of binary search tree as the tree given to us is BST, and we could solve a solution in much more, lesser time complexity. So let's visualize this process. Okay, let me draw the tree first. So this is the binary tree I have drawn for you. Now let's look and visualize the process. So what we could do, okay, we could start from the root node and compare its value with the val. Let val be, um, let's take a guess. Let it be 18. Okay, we're looking for 18. That's fine. Let's do. So if the current node value is equals to val, we return it immediately, right? That's the concept. If we found a target. But now, if you could see, we're standing here and 20 is greater than 18. Okay, which means that if I go to the right tree traversal or the right subtree of the 20, I will get value which is always greater than 18. Correct? 25 is there, 22, 28, 24. So no use of traversing here. So we will use the binary BST concept, and I will say that, okay, I will go to the left subtree of this 20 node. So I will come to this particular part. Now, now, if I come to this particular part, I can see that I have value 15 also, 13, 18, 12, 17, 19. So I have the 18 here, but our traversal doesn't know it, right? We know it by saying it through the visualize process. But let's see, now we're standing at 15, okay? We see that 15 is less than 18. Okay, but from that we know that if I go to the left subtree, I will get values which are lesser than 18 or 15. So which is eventually less than 18, right? So no use of going to the left subtree. So what I will do, I will try on going to the right subtree. So I came to this particular part of the tree. Okay, so I'm in the right subtree here. So now I can see that 18 is equals to 18 here, right? What I will do, I will just return node. That's all. Not value, just node. So it will return this complete subtree. So this is what we can do in our intuition, right? So that is what it is written here. A value is greater than the current node's value. The target must lie in the right subtree due to BST rules, which we did. If value is less than the current node's value, the target must lie in the left subtree. Definitely, if value, since your value was 18 and I was standing at 20, so it will lie in the left subtree. But in this case, 18 was greater than 15, so I knew that it should lie in the right subtree. That's all. We keep repeating this process, moving left or right until we find the node or we reach null, right? And here we will try using while loop instead of recursion because it will make it more iterative and much more faster because iteration are much more faster than recursion in general, and memory will be much more efficient. No stack space will be used. So this is much faster and it will be easier. Okay, so we have figured out that we will use the concept of BST here, and it is pretty easier to solve, right? And we will use iteration, which is a while loop rather than recursion to make it much more faster. Okay, but how we gonna simulate this, right? Let's look at that. We will start with the root node. Let me draw the tree. We will start with the root node or the as the current node. Okay, this let it be the current node because we will start from somewhere, right? And we will check if the value which was given to us, if it is greater than the root value, or whether value which is given to us it is less than the root value, or whether the value which was given to us it is equal to the root value. Which one is true here? Greater than, less than, or equals to, right? So we will do this thing. We will compare this while the root does not reaches null. Okay. If root comes here and it reaches null, that's all. We are done with the iteration and we'll just stop it there. Otherwise, we will if the value is greater, the current value, which means that we have to go to the right subtree. Suppose if you remember this was 20, right? And suppose this is the current value, and it was 15 in this case here if you remember, and we had 18 in our hand, right, to be searched. Since 18, which is the current root which was the value to be searched, was greater than the root value, what we did, we moved to the right, because if we went to the left we will find much more lesser value than 15, right? But in the right we might get value which is greater than 15 or equal to 18, right? So we go to the right. But if value is less than root value, in this initial case it was 20, right? Current value was root value was greater than the given value. So what we did, we moved to the left, because if we move to the right we will get much more greater value than the given node or current node, right? But in the left we might get value which is equals to 18, correct? And if at the end, when we find 18 in one of the node, we just return the root value. That's the case. So if we find a root node with value equal to the value given, we return it. This is a subtree. Okay. The loop ends without finding the value, we return null. So if basically the loop ends and we are at the null here in the leaf case, we'll just return null. That's all. It's pretty simple implementation of it. What we figured out? The key idea is to leverage BST structure to avoid unnecessary traversal, basically using the concept of BST when the BST is given to you rather than using BFS traversal or traversing the complete tree using BFS or BFS. Okay. By comparing the branching left and right accordingly, this is also the concept of BST, looking for the left and right subtree, which value is greater and which value is smaller than the given value. Reduces the time complexity. To use an iterative loop instead of recursion to avoid stack overflow or deep trace. Since this solution could be done with the help of iteration only, We don't need any recursive solution and storage and have extra space or stack. Okay. So iteration will be much faster than recursion, of course, in general cases. So this is the intuition all about. I hope you understood everything. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach and how we're going to solve it. We'll start with handling a base case and initialize search. Okay. If root is null, we return null immediately since the tree is empty and there is nothing to be searched. This is a common base case in every tree question. If the tree is not given to you, first of all, or if you reach at the leaf node and if you check for that if root left is or right is null, we just return, right? There's no use of doing anything. We just return in that case. Okay. Otherwise, we start at the root and begin traversing the tree. We use while loop to iterate through the tree without recursion. That will be done using while node or while root, whatever the variable we have used there. Okay. And at each step, we compare the current node's value with the target value, which is basically this logic which we understood here, this one. Okay. While we are doing this, we want to leverage BST properties to minimize unnecessary traversal and avoid extra space lying like stack or queue. Okay. Because if you use BFS, we need queue with it, right? If you remember. And if you use recursion, we need stack space, which is automatically generated while using recursion. Now, in the step two, we traverse the tree iterate. Now, in step two, we traverse the tree iteratively using BST rules. The loop continues as long as the current node is not null or the node's value does not match the target value. For example, if this is the tree. Just keep in mind what could be the edge cases or the end cases. If you reach to the null, okay, this is the leaf node part. If you reach here, okay. Otherwise, if the value is not present, if value is not there, then also we won't iterate, right? Until and unless we don't face any one of these conditions, we keep on iterating. And inside the loop, what we do, if the value is greater, value given to us, if it is greater than the root value presently, we will do what? We will go to the right side. Root equals to root dot right. And if the root value, if it is less than the root value given, if the value given is less than the root value given, we'll go to the root left. Okay. This is what written here. And why we do this? The BST rule ensures all the values in the left subtree are smaller and all in the right are larger. Okay, we use this thing. We eliminate the half the tree at each step. Okay, half the tree how? Because if you're standing here and if you know that you have to go to the left subtree, this complete tree is discarded, right? This complete subtree is discarded. So we are in the half leftover tree. In step 3, we return the result. The loop stops when either we find a node with a value equal to val or we reach a null node, meaning value does not exist in the tree. We return the current node, which will either be matching node or null if not found, which is basically we will just return root. That's all. So I hope you understood this approach explanation. Now let's move to the next slide. The code is the exact copy of the approach we discussed. Let's understand it line by line. If you could see, we have a function BST, okay? And while we have written here in a base case or while loop condition, while root is not null and root value is also not equals to this particular value, we keep on iterate. If value given is greater than the root value, we go to the right subtree, else we go to the left subtree. And after this complete iteration is done, we just return the root. It's pretty simple, straightforward code. The time complexity is O of log n. Reason being, in first iteration you moved left, so you discarded complete one of the part of the tree, right? So it is basically n by 2. Then this n by 2, you went to the one of the halves subtree, divided it by 2. So it became n by 4. And this again was divided by 2. So it became n by 8. Similarly, it went on, right? That's why when the things are divided into n by 2, the time complexity is basically log n. Okay. And space complexity is O of 1 because we are not using any extra space or any extra stack space in our program. Okay. I hope you understood this code explanation. Now let's move to the next slide. Now, since we have the understanding of the code, let's look at the dry run of the example. So I have taken this example. So I have drawn the tree already. Now let's look at the dry run. So I have taken while root is not null and root value is not equal to the value, and here it is given null. Okay. a value given is fine, 5, okay, but let us take to it to be a in this case let it be 3, okay, we're looking for 3, so our value in this particular case is 3, okay. So what happens now is that we're standing here and we check if the given value, which is 3, if it is greater than the root value, which is 4. But here you could see that value given is 3, okay, it is greater than 4 now, but the value which is given is less than 4. It means that 3 is all will be present only in the left side of the left subtree of this particular node 4, correct? So what happens? We go to the root left as per our condition. So we come to this particular subtree. Now we're standing at 2. Now 2 here, if you could see, 2 is the root value and it is smaller than 3, correct? Which is a given value. What happens when val is greater than root val? We go to the root right. So we come to the right subtree. We're standing at here now. Okay. Now we can see that value is 3 and current node is also 3. It is not greater, not smaller. So what we do, and it is also not equals to val, which means it is equals to val. So this condition gets false. Okay, so we run out of the loop and we return the root. So in this case, we return 3 as the output. And if you can check, 3 should be our output when our given value is 3. Okay, you could take a bigger tree and do the dry run by yourself. And if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the BST concept, the approach, and the code. After that, do a dry run by yourself on 2, 3 examples of a bigger tree. And I'm pretty sure you will understand both the solution and the thought process behind it. Now let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. While we'll start with writing while root is not null and root value till when it is not equal to the given value. If the val given to us is greater than the root dot val, what we will do? We will go to the right subtree. Else, we'll go to the left subtree. And when the iteration is completed or we find the value which we're looking for, we will just return the root. Let's try submitting the sample test cases. It got submitted. Let's finally submit the solution. We have successfully submitted our solution. Now, code of the problem is available in the GitHub repository. You can find the link in the description. Thank you, everyone.